Hi, so in this video we are going to continue our discussion on simple linear regression analysis. So the basic research question that we are facing is to examine the relationship between two quantitative or numerical variables, x and y. So if that is the basic question, then there are basically three ways to analyze that relationship. One is to just to visualize using a scatter plot. And the second method is that what we discussed last week, which use Pearson's correlation. And we talked about two different equations. One focuses on the z-scores, and the other one focuses on the shared variance. Correlation is a ratio between how much variance is shared between two variables divided by how much variance is there in the two variables by themselves. So there is a third method that we can examine the relationship, summarize the relationship, which is regression analysis. And we already introduced the so-called simple linear regression last week. And the simple linear regression takes the form of a linear function, and you can visualize that as a straight line that goes through the center of the scatter plot. And it takes the form y prime equals a plus bx, and y prime is the predicted value of a y variable, the criterion or the outcome variable, and x is the predictor, and a is the constant, or you can say that's the y-intercept. So basically, what a is, if you kind of extend this regression line until it intercepts with the y-axis, so if that's 0, x equals 0, and this part essentially is the value of a, because that's the predicted value when x equals 0, so y prime equals a. So that's the intercept. And the b, on the other hand, is a slope. So the way to think about b is that it's a ratio of how much change is in the x compared to how much change is in the y. So that provides the slope. All right, so that's the basic of the regression analysis. And next, let's talk about the equation. So how do we calculate a and b? So given that this is a regression equation, what we need to find out is the value of a, right? What is the value of the constant? And also what is the value of the slope or the regression coefficient? And we already introduced the equation for b coefficient last week. So b equals r, correlation coefficient, between x and y, multiplies standard deviation of y divided by standard deviation of x. So it has something to do with r. So to what extent the two variables are related. So the higher the correlation, the more steep the slope is. And if r equals 0, x and y are not related at all. In that case, r equals 0, the slope b equals 0. So you're looking at a line that's basically parallel to the x-axis. Meaning when the value of x changes, the value of prediction y does not change. Okay, so that is how we calculate the slope or the regression coefficient. Now, we would always calculate b first because the equation that we use here needs the item b. So we estimate b and then we calculate the constant. So constant equals the mean of the dependent variable, subtract b times the mean of the predictor. Okay, so once we figure out b, if we know the mean of x and the mean of y, we can calculate the a. So once we have the value of a and b, we have the regression equation. Now, what can we do with the regression equation? So one of the things that's nice, that's great about regression analysis, of course, is that it allows us to make a prediction. Meaning, if we know the value of x, we can make a prediction about what the y should be. Okay, so regression is kind of different from correlation. Correlation describes the relationship, but regression analysis takes one step further because it allows us to make predictions. So we are going to, in the second half of activities 13-2, it's a separate video, we're going to use these two equations, actually going to use these two apply these two equations and do some calculation, but that's going to be in a different video. Okay, so calculate A and B, conduct regression analysis. Okay, so the last topic we're going to discuss about regression analysis is the so-called least squares criterion. The kind of simple linear regression analysis that we talk about in this class, including if in your next class, next stats class, Psych 121, or even in Psych 102, when we discuss multiple regression analysis, multiple linear regression means it's a linear regression. We're still trying to predict a quantitative and numerical variable, but we have more than just one predictors, right? So instead of x, we have x1, x2, x3, and the regression equation becomes y prime equals x plus a1, x1 plus b2, x2 plus b3, x3, etc. So we kind of mentioned that last week. And so all these different kinds of regression analysis are all called the least squares regression. Okay, it's the term for this kind of regression analysis is called the least squares criterion, least squares regression. Another way to think about it is that they are regression analysis that uses the least squares criterion. So what is the least squares criterion? Well, for that understanding, we have to start from this concept, this idea of residual. And the definition of residual is this. It's very straightforward. It's the error of prediction. So let's say for a particular x variable, let's say you have a subject who has x equals certain value and y equals certain value. So you have actual measured value of y. Now, if you have a regression equation, you can just plug in y prime equals a plus bx, and then you can calculate the value of your prediction, that's y prime. Now, y prime does not always, usually it does not exactly equals y. So there's a difference between y and y prime. And the difference between y and y prime, between its original values, the actual value of y, and the prediction is the error in prediction. And so you can use the term error in prediction, or we can use the specific jargon, it's the word residual. Okay, so residual is just error of prediction. So how do we calculate the residual? Simple, it equals y minus y prime. So that is residual. Now, this is the way to visualize what a residual really is. So let's consider this subject. Okay, so the position of this data point, this dot, is determined by value x and y, right? X and y. So let's say I'm just going to make up some numbers. So let's say this is 5. Just going to draw something. Okay, so these are the certain values, and then you also have certain values on the y-axis. Let's say this is 1, this is 2, this is 3, this is 4, and on the y-axis you have 1, 2, 3, all right? And of course, this is 0. So we have, let's consider this particular dot. Okay, so the position of the x and the y, let's say x roughly equals more or less, let's say 1.8. Okay, so x equals 1.8. Right? And what is value of y? So we're talking about this dot, right? So what is the value of y? Let's say more approximately, let's say 2.5. Okay, so for this particular case, x equals 1.8, and the actual value of y equals 2.5. Okay, so if we draw this vertical line, kind of think about like what is this section of the line? Well, this is the vertical distance of this data point from the regression line. Okay, so we kind of intercept from here. So if we continue extend this line, it goes on to the x-axis. So that's when you hit, okay, this is 1.8. So x equals 1.8. But what is this value? What is the coordinates of this dot on this regression line? Well, this, it turns out, this section is y prime, right? And of course, in this case, we just estimate the value of y prime equals more or less 1.5, right? So y roughly equals 1.5. But if you have the regression equation, you would calculate y prime equals a, whatever the constant is, plus b, whatever the slope is in this particular case, times the value of x, which is 1.8. Okay, so you plug in the number x value into the regression equation, and you do the calculation, and y prime, it turns out, is 1.5. Okay, so for this particular case, the actual value of y equals 2.5, and our prediction based on the x value equals 1.5. So what is y minus y prime in this case? Well, y minus y prime, 2.5, subtract 1.5 equals 1. So what is that value 1? Well, it's the residual. It is the residual. It is the error in prediction. Okay, so as this, if you think about this diagram, some of these errors are residuals, are positive, meaning we over predict. The predicted value is actually the predicted value is lower than the actual value of y of the criterion variable. But for some other data points, we for this particular case, it's under predict, right? So the predicted value is lower than the actual value. But for some other data points, for example, for this particular data points, we overestimate, meaning the prediction is greater than the actual value of y. Right? So, meaning some of the error prediction, some of the residuals are positive, some of the residuals are negative. And it's very easy to kind of just visualize. So what exactly in kind of another way to think about the residual is that they're just the vertical distance. They represent the vertical distance of these data points from the regression line. Okay, so each of these vertical lines, line segments, represents the residual. And for this particular data point, there was no error in prediction because this dot sit exactly on the regression line. And so is this dot. There's no error of regression. But overall, you have some errors. Now, this is kind of a very interesting idea. So if you think about it, well, some of these errors are positive, some of these residual, some of these errors are negative. What happens if you combine all these errors of a prediction? So what is the sum of x of y minus y prime? Okay, so what is the sum of y minus y prime? Well, interesting enough, the sum of all residuals equals 0, which should remind you of something. We had something discussed earlier in the semester. Something, subtract something, and then you add them together equals 0. Okay? It looks very, very similar, and also, in fact, we are talking about the exact same idea. So if you think about x minus m, right? Sum of all deviations equals 0. And in this case, instead of x, we have y. Instead of a mean average, now we have the prediction. Now, here's another realization. So what are we predicting? So when we use a linear regression equation to make a prediction, what exactly are we predicting? We are predicting the average. Okay, so essentially we're saying if for this x value on average, y should be this value. And for this x value, the average y should be this value. So when we make a prediction, we are in fact making a prediction. The predicted value is in fact is the average. It's the mean. Okay, and so follows that from that idea. The next we have two more concepts which kind of make sense. And if we add all these residuals together, then obviously, if we want to have an overall measurement of error, how much error is in prediction, we cannot simply add the residuals together because it's always going to be 0. So how do we get rid of 0, get rid of the negatives? Well, the answer is the same thing. We just take the square of the residuals. So sum of square residual equals sum of sigma y minus y prime, take the square. That's the definition of sum of squares. Again, this is something we look very, very familiar, right? And finally, we are ready to discuss what is the least squares criterion. So basically, when we conduct linear regression analysis, we try to find a set of value A, constant, and B, slope, such that the overall, the combined error of regression is the lowest. Okay, so that combined, the total error of regression, total residual, is measured as the sum of squares of residual. So that criterion says we want to make this item, sum of squares residual, as small as possible. Okay, so that's why this kind of regression analysis is called the least squares criterion. In this word, the squares is a shorthand for sum of squares. We try to minimize the error in prediction. And the equations that we discussed in the previous slide, B equals R times S, standard deviation of y divided by standard deviation of x. And we also have a different equation for A. Those two equations are worked out by mathematicians over the years, that if you apply those two equations, it guaranteed the result that we obtain, the regression equation, y prime equals a plus bx, provides the best regression function that we can have. Now, what do we mean by best? The lowest error of prediction, as measured by the sum of squares of a residual. Okay, so that's why it's called the least squares criterion. Now, a little more on this idea of the let's say the distance. The residual represents the average distance from the it's the vertical distance from the regression line. So that also implies that if you think about what is the shape of residual, it's kind of the relationship between what a scatter plot look like, what the correlation coefficient is, and how much information that we can predict. That is actually all related to the idea of that all related to the idea of residual. Okay, so here, let me click a couple of things. No, into that. Then we need to have a regression line. Okay, so this is the scatter plot based on the correlation R equals 0.50, and so we have these data points, 60 data points, and this is the regression line. Essentially, this is the regression line that cut through the middle, the center of this scatter plot. Now, think about these distances, vertical distances. Okay, so this is a correlation of 0.5, and you have these numbers, these data points all over the place. Now, think about the average distance. Okay, the distance of these dots, the vertical distance from this line. Remember, the distance is a measure of residual or error in prediction. So what happens when correlation increases, let's say from 0.5, let's say to 0.7? Okay, so what happens to the average distance of these dots from the regression line? So this is 0.5, this is 0.7. What if the correlation equals 0.9? Okay, they're getting closer. They're getting closer to the regression line. In other words, when the correlation increases, the prediction gets better and better, in the sense that the error, so residual, is going down. Okay, and what happens if the correlation goes even higher, 0.95? Now they are even get closer to the regression line. The residuals are getting smaller and smaller. What if the correlation equals 1? Then all of a sudden, all the dots are positioned exactly on the regression line. In other words, when correlation equals 1, there is no error in prediction because the vertical distance of these dots from the regression line becomes 0. Okay, so if all the residuals are 0, then sum of squares of residual equals 0. In other words, there is no error in prediction. The same thing happens when you have R equals -1. Right, this is -1. Again, all the dots are located exactly on the regression line. So again, there is no error in prediction. And you can change the size of the correlation, getting closer, getting smaller and smaller. So as the correlation gets smaller, the lines, those dots, are moved further and further apart from the regression line, right? From the regression line. Okay, so that is kind of gives a very nice illustration of the relationship between this scatter plot, what a scatter plot should look like, versus the size of the correlation versus the size of error in the prediction. And here's another, just to summarize what we just talked about. So correlation equals either 1 or -1. Regression is perfect, meaning there is no error. So sum of squares. So in this case, sum of squares residual or error equals 0. Right? This is another example in which the sum of squares residual equals 0. Right? And this, of course, obviously is not 0, but and this is a situation you have the distance from the vertical distance from the regression line is much higher compared to this situation when R equals 0.8. On average, these dots are much closer to the regression line, meaning the error is smaller in this case. So finally, let's think about some of the equations that we have discussed so far. So these two equations you should all look very familiar. This is ANOVA. We're talking about analysis of variance, one way between subjects, right? So in that analysis, the total sum of squares, the total change in the dependent variable equals sum of SS between plus SS within. So this is the treatment, the independent variable, and this is the error. And of course, if we conduct ANOVA, we have an effect size measurement, which is eta squared between sum of squares between divided by sum of squares total. We usually draw eta squared kind of in this way. It's one part of this sum of squares total can be attributed to SS between. So this is the proportion of total sum of square that goes can be attributed to the treatment effect. Now, what about regression analysis? Well, regression analysis, we have something very, very similar. So in this case, we have sum of squares total. So the total sum of squares, total amount of variation in the dependent variable, in the criterion variable. And the total sum of squares can be divided into two parts. One is sum of squares error, or that is sum of squares error is just another name for residual, right? So this is residual. Okay, so that's SS residual. Now, if you combine what cannot be predicted plus what can be predicted, what you have is SS total. So another way to think about it, what happens when we minimize SS error? What happens to SS regression? Well, if this is the lowest, you go as low as possible. This goes as high as possible. So when this is minimized, SS regression is maximized. And in regression analysis, it's the index that we use to calculate how much we can predict. It's called R squared. It's always a capital R squared. It equals sum of squares of regression divided by SS total. So if you want to have a visualization of what this is, it's very, very similar, but we usually draw the line in this. Okay, so think about what is R? What is the definition of capital uppercase R? R is a correlation, Pearson's correlation between two items. One is Y, and the other one is Y prime. So in other words, this is a correlation, Pearson's correlation between the actual value of the dependent variable and the predicted value of the dependent variable. So if this is a Y, then this is Y prime, and this is the correlation between Y and Y prime, so this part is R, capital R squared. And when we conduct either multiple regression or simple linear regression analysis using SPSS, this is one of the statistics that SPSS would provide. And then we use R squared as indication of the effect size. So how much information we can predict. Okay, how much information that we can predict. And if we conduct a simple linear regression, okay, this happens only if you conduct a simple linear regression analysis. R squared, capital R squared, how much we can predict, happens to equal R squared, the correlation between X and Y. Okay, so R is correlation between Y and Y prime. So it's the same relationship. So how much relationship do we have? What is the strength of the relationship between X and Y? That if all that information, if all that relationship is captured by your regression, the maximum, that's the same R squared. Okay, so if they share 25% of variance, how much variance we can predict maximum? 25%. Okay, so a final item for this slide is this Very curiously, it's a summary table. It's called ANOVA. When we conduct a regression analysis, we always use a test to indicate whether the regression is significant or not significant. Curiously enough, we use the ANOVA for this purpose. So this is an ANOVA summary table. Everything looks very familiar. We have let's see, we have sum of squares, we have degree of freedom, we have a mean square, we have F, and we have level of significance. Now, the only thing that's a bit different when ANOVA is used in the context of a regression analysis, it's in the terminology for the source, right? So total, that's fine. We always have total. If we conduct a between subjects ANOVA, this would have been between, right? This would have been between. And this item is used called within or error. Now, in the context of regression analysis, they are being called for something else. So instead of between or the independent variable, the treatment, now we have regression. Instead of a within or error, we have residual. So the SStotal equals SS between plus SS within. Here we have SStotal equals SSresidual plus SS regression. Right? So 6.25 plus 53.943 equals 60.195. Okay, so again, we have this kind of very nice relationship. This is a kind of just, by the way, regression analysis and analysis of variance, they're essentially the same. The underlying mathematics are the same. So that's why R squared, capital R squared, is interpreted as eta squared, because they are the same item, they are the same thing, just being called by two different names given in two different contexts. Okay, so this is the end of this lecture. So in the next video, we are going to go over the second half. We're going to go over the second half of activity 13-2.